involved with that lab. Also due tomorrow, you come to lab this week, the unknown lab report is due. Any questions about that? I sent out some answer keys this morning to some of the various problems. Okay, they should be labeled in the file name. Did we run out of that handout? Actually, I may have had some upstairs extras that I meant to bring, and I did not get them. I can get them at halftime today. Please remind me, who did I get one? Just a few. Okay. Yeah, and I think I had some. I'll leave these in here to remind me. Okay, Fisher projection. Fisher projection, we would like to be able to just have more time and not have to erase all that we had up there. You know what, I'd like to just kind of redraw them maybe. Back up here. Fisher projection of Roman numeral 1. What side was the OH on? Roman numeral 1.
On the left.
OH was over here?
Yes.
Which side was the chlorine on?
On the right. Right there.
On the right? Is that Roman numeral 1?
Yes.
Did we draw all 4 or did we just draw the number 4?
Number 4.
Number 4 was number 4 the enantiomer?
Yes.
Well, if it was the enantiomer, the H was here, the OH was there, chlorine was there, and the H was there. Roman numeral 4. Those look like enantiomers. Indeed they are. That was a DL pair. Did we draw Roman number 2? Okay. We did perspective drawing of number 2. Perspective drawing, I'll put it here, you should have these. Number 2, perspective drawing. The OH was what, bolded? Yeah? And the chlorine was? Let's draw this one in a Fisher. We're doing this a little bit convoluted here. Hopefully everything is going to be straight in your notes here. This is Roman numeral 2. This is called perspective drawing, where we show the full stereo view with dashed in bold. This is Fisher projection. Let's draw this. We're going to put the OH at the top carbon. So that OH is the top carbon. That means this is the ground. If that's the ground, and okay, and that one is above the ground, this one's closer to the ground. We're looking at this with our feet on the ground. With this methyl going away, with that methyl going away, the OH is on my
Left.
coming out.
Right.
It's on my left. There's The methyl going away, which that's what that means, the OH is on the left. That means the undrawn H, which is going the other way, is on the right. Okay, where do we put the chlorine at for number 2 here? With this methyl going away, which is that's what that means, that methyl's going away. Top and bottom is going away, things on the side are coming towards it. The methyl going away, how's the chlorine?
On the right.
The methyl going away, the chlorine is on the left. Why did you say right? Who said right? Methyl going away, the chlorine is on the left. The undrawn H is over here. Who said right?
I did, because I thought
So why do you
when
think
you're
it's
looking
right?
up this way, that chlorine will be in your, oh, yeah, it was left.
But you should not be looking over here. If I'm over here, is this methyl going away from me compared to the carbon? No, the methyl's coming this way. I don't need to be over here. I need to come over here instead. Feet on the ground though. Looking through here. All right? Here's the carbon. Is the methyl going away from me, away from that carbon, or towards me? If I'm over here.
Away from the carbon.
That methyl is going away from me if I'm over here. With the methyl going away, the chlorine is on my, it's going back, that's what the dash means. I'm over here, the chlorine's on my left. I'm just drawing what I see. The methyl's going away, chlorine's on the left.
So if we can draw from either view that we're looking at, so basically that can be turned upside down and it'll still be correct.
You could, but, so you want to have the ground up here.
She wanted to be a bit true. Okay.
You could put the ground up here. Doesn't matter, it's going to be upside down. And the OH would be closer to the ground. Right now the OH is away, here's the ground's down there, the OH is further away from the ground. I just do it like that. Why would you want to flip it?
No, I was just asking a question.
You could, I just, because if the ground is up there, then I've got to stand like this. If the ground is here, like that, I can stand on the ground and be like I'm standing here. It's just I'm like this a little bit. But the methyl's going away. Oh, there's the methyl going away. It's going away from this carbon, this chlorine is on my left. I can draw, I can make models of these. Here's the backbone. OH is coming forward. And the chlorine is going back. Chlorine will make green. There it is on the board. The black is drawn flat on the board. OH is coming towards you, right? Chlorine going away. Okay? Well, let's just look at it. With this methyl coming away from me, which side's the OH on? Well, right now this methyl is not going away from me. It's coming towards me. Now your book may tell you to rotate it. I'm telling you to go over there because we can't move it on the board. If I come over here, now the methyl's going away from me. See it on this carbon going away? With it going away from me, what side's the OH on? I'll show you what I see. That's what I see. With the methyl going away, the OH is on the left. Right? Here it is on the board. Okay. With this methyl going away, what side's the chlorine on? Well, I don't need to come over here. Because I'm over here, this methyl ain't going away from me. I need to be here. With the methyl going away, what side's the chlorine on? On the left. I'll show you what I'm looking at. Right there. With the methyl going away, chlorine's on the left. Here it is on the board. Now, on the board, both methyls are going away. That's what Fisher means. Tains the top and bottom. This has to just be rotated. But if we rotate it, now are both methyls going away from you compared to the carbons? Yes. And with both methyls going away, which side's the OH on? Here. And which side's the chlorine on? Here. So there it is. Yeah. This is that compound shown either like that. See, if you twist this down, the OH, well, that's not the OH. The OH is blue. Right? OH is forward, chlorine's back. But here it's drawn, this middle bond is drawn vertical, and that's back, and this is back, and when you draw it like that, these two guys are both over here. Now, we can add some terminology here between 1 and 2. What's the relationship between 1 and 2 again? Diastereomers, because are they enantiomers? No, they're not mirror images. They're stereoisomers that are not mirror images. That's diastereomers. If they're not mirror images, then they're going to be diastereomers. There's some terminology to distinguish between diastereomers here in Fischer. When the high priority groups are on opposite sides, what's the high priority group on this carbon? O on this carbon, chlorine. When they're on opposite sides in the Fischer, it's called 3O. When they're on the same sides in the Fischer, it's called erythro. The enantiomer of number 1 is over there, number 4. What would you call that one? The enantiomer?
3.
Also 3O. The mirror image of 3O is 3O. So we have other terminology. We can do number 3. I'll erase this because we got more room. One, 2, and 3. First perspective drawing. Number 3 in the perspective. Number 2. Number 3 over here. The OH was probably dashed, wasn't it? And the chlorine was bold. Okay. If we draw this in a Fischer, what's the relationship between 2 and 3? 2 and 3 are enantiomers. Everything is switched. Backbone's the same. Everything is switched. Well, you can cheat. We can cheat. Draw the enantiomer here of that. Wouldn't it be H here, H here, methyl there, OH here, chlorine here? Do those Fischers look like they're mirroring? Yeah, that's the enantiomer. You look at this, with the methyl going away, which side's the OH on? Well, obviously right. Well, look at it. Here's the ground. If we look at it with, if that methyl's going away compared to the carbon, the OH is on, it's going back. So if I'm over here, back is to my right. Okay? If this methyl's going away, where do you want to stand? You want to stand over here. With that methyl going away, which side's the chlorine on? On the right. See, they're both on the right. We kind of cheated because we had this one. This is erythro because the high priority groups are on the same side. The enantiomer is also erythro. mirror image of a erythroid is erythroid. This is somewhat analogous to cis and trans, but this is the terminology used with fissures. Cis and trans usually only works when it's fixed. This is actually fixed, but it's fixed in the fissure. In real life, though, it can rotate. Is the OH in the methyl? Which compound is this? I can't even remember. With both of them going back, it is the number 2. Okay? Is it cis or trans? Cis or trans? Cis? What is it now? Well, it can't be both. It has to have a distinct stereochemical descriptor. Is it cis or trans? It doesn't work. Whenever you have free rotation, cis or trans doesn't work. Okay? And another way to say that is cis and trans is only used when it's fixed. This can actually freely rotate. Is it cis or trans? Well, what is it? Well, here's what we do. When drawn in a fissure projection, are the groups on the same side or opposite? There's only one answer here. When this is drawn in a fissure, like that on the board, they're on the same side. When drawn in a fissure, same side, thus we can call it erythro, because it's based on when drawn in a fissure. Okay. Now if we go to both of them OHs, let's look at 2 and 3 with both being OHs. That's number 3, right? If we change these to OHs, what's the relationship between these two? Relationship between those two compounds. Enantiomers? Why do you say they're enantiomers?
If they mirror each other the same, like they just have flip configuration.
Split configuration?
They're mirroring each other with completely flipped configuration.
Okay, oh, you said flipped.
Yeah.
I agree they're mirroring each other. Does that make them enantiomers? I mean, these two paper clips are mirroring each other. Are these enantiomers? No, they're the same thing. So, yes, they are mirroring each other. Same or different, though? Same or different? Who says they're the same? Okay. Why do you say they're the same? Ah, you see a plane of symmetry. And if we can find a plane of symmetry, what does that tell us about the mirror image? Same thing. Like those paper clips. The reason they're the same thing is because if something, where's Waldo? If it has a plane of symmetry, the mirror image is the same thing. Okay? Now you can make model of both of these, and I'll guarantee you that they will superimpose. It will be the same molecule. Okay? So, this is called a, if these are the same, there's actually only three compounds here. 3 stereoisomers. Only 3. Now there's 2 chiral carbons, there's 2 stereogenic sites, that would tell us 2 to 2 is 4. That's maximum number. There's less than max here, there's only 3. Why? Because 2 of them are actually the same thing. This would be 1 DL pair. and one meso compound. That's called a meso compound. A meso compound is a compound that has chiral carbons. Everybody agree it has chiral carbons? It's got 2 chiral carbons. But as a whole, the compound is not chiral because it has a plane of symmetry as a whole. If you remember, we said if a compound has 1 chiral carbon, it's going to be chiral. What about if it has 2? It doesn't have to be chiral. If it has 2, actually, if it has 3, 4, 5, it only with 1 does it have to be chiral. If it has more than 1, it could be meso. All right? This is meso. That's 1 compound thing. So you can't count that as 2. That's just 1. Meso goes with, now you may be tempted to call this erythro because they're on the same side. But instead of calling it erythro, we call it meso. That's more meaningful. But see how easy it is to see the plane of symmetry in the fissure? I mean, that's a straight cut through there. The same is here, the same is here. Right here. Can you see a plane of symmetry here? It's a little bit difficult to see it. If you first draw it in a fissure projection, now it's easy to see. Change this to blue. Right here, this is with both OHs, so that's both OHs, yeah? There's the plane. This OH going back, this OH coming forward. OH, there it is. You see a plane of symmetry? Can you cut right through there? Is that a plane of symmetry? No.
No.
But look, if we rotate like that, now do you see a plane of symmetry? Right through here. Same on this side, same on that side. But guess what? When we put it in a fissure, we effectively rotated it because now, there it is on the board in a fissure. Both methyls going back, both OHs on the right. And the plane of symmetry we drew is right through here, horizontal. Same, this top is mirroring the bottom, mirror plane. By the way, here's a little trick. We're looking at the compound with the OH here. What was R and S here? Let's do that again. Oxygen 1, carbon with oxygen would be 2, carbon would be 3. H here is coming forward. What is this? That's S. That's S, yeah? Real quick, what is this over here? How do you know it's R? No, you gotta be careful about that. It depends on the backbone. Yeah, it depends on. You have to be careful about that. I think you just have a 50-50 chance of being right in that. Now, this over here is R. I don't know it's R. I mean, I can do it. Didn't I just say there's a mirror plane between the two? Isn't there a mirror plane here, really? You can't see it here, but you can see it here. But if we know there's a mirror plane, what's the mirror of S? R. That's one way you'll know a meso compound. It's an internal mirror plane. This side is mirroring this side. See, over here you got a carbon with an OH and methyl. Over here you got a carbon with an OH and methyl. But they're just inverted. That has the S configuration. If this is a mirroring of that, if R looks in the mirror, what does it see? S. Okay? If this was RR, I would know there would be no mirror plane there. Because the mirror of R is not R. All right? Okay, we went through that 2 separate days and hopefully get that organized. Ultimately, it's good to struggle to organize it. That's where you learn. Okay? If it's presented very cleanly and all, you just kind of stare at it, I feel. Okay? Your job is to put it all together and arrive at your understanding. Okay? I think the other handout white handout, is that right? How are we doing on the alkene puzzle? Anybody got the riddle solved yet? Still working on it? How was the alkene able to learn all of its electrophilic reactions? Good review there. The white stereochemistry handout. Look over in the back a little bit. You'll see a page that shows all your common carbohydrates. Well, guess how carbohydrates are typically shown? They're shown as Fischer projections, okay? Now, carbohydrates can vary a number of carbons. Most common is your 6-carbon carbohydrates, like glucose, okay? And of the 6 carbons, 4 of them are chiral. And so we got 4 crosshairs, all adjacent to each other. But you can also have 3-carbon carbohydrates, or that's just 1 chiral carbon. By the way, this does use D and L, but the capital D and capital L is different from little d, little l. I'm not going to explain capital D, capital L. All right? But it is different. Capital D is older and is different. It's still kind of used though. I think it's mentioned, described somewhere here. If you look at the 4-carbon carbohydrates, there's 2 possibilities. You draw it like this. The 2 OH groups can be on the same side, or they can be on opposite sides. Same connectivity. Everything's connected at the same spots, just projected differently. So these are stereoisomers, right? What type of stereoisomers are they? There's only 2 types of stereoisomers, enantiomers and diastereomers. What type are these? Diastereomers, because that's obviously not the mirror image of this. Now this is called erythros. When the OH groups are on the same side, erythros. When the OH groups are on the opposite side, threos. That's where the terminology erythro and threo came from. Because it matches that scenario. So what is the relationship between these two? What type of stereoisomers are these? Diastereomers. Yeah, everything here is diastereomers. Look down below. What's the relationship between all of these carbohydrates? They're all diastereomers. Look at one, this, allose and altrose. What's the difference? One carbon has been switched from R to S. Are these enantiomers? No, enantiomer, everything would be switched. There's no enantiomer of allose shown up here. These are all diastereomers. Here's a new term, epimer. Epimer is where you only switch one chiral center when you have multiple. So these can be called epimers. Epimers is a specialized class of diastereomers. What about glucose? Is glucose an epimer of allose? Yes. These two are both epimers of allose. You can also sometimes denote what has been changed. That's called C1. That means C2. So this is called a C2 epimer of this compound. But glucose is called a C3 epimer. That indicates what has been changed. The C3 tells you where, and epimer tells you one thing has been changed. The C3 tells you where. Okay? Terminology. What about mannose? Is mannose an epimer of allose?
No. It's got two.
No. It has two changes in configuration. So it would not be called an epimer. But it is called a diastereomer because it's a stereoisomer that is not a mirror image. Okay? So in biochem, you'll learn carbohydrates and you'll see Fischer projections here in a bit. All right? Let's get back, I think, to the purple. We have next page. Number 3, I think we've already kind of covered that, yeah. Chiral center versus stereogenic center. An alkene can potentially be a stereogenic center. Consistent trans is possible. Let's look at alkene a little bit. How are we doing with alkene nomenclature? Blue handout, yeah. By video, any questions over there? What did we not cover in the video? Did we name these compounds in the video?
Yeah, the top one.
We named this one?
Yes.
Did we name these?
Yes. Yeah.
Did I name it in the video?
Yes.
Yeah, I remember that.
Yes.
I named that one? What about this one?
Yeah. Yeah, you
You named all of those? Okay. Stereogenic, is this alkene stereogenic?
Yes.
Tell me why it's stereogenic. It's trans here, could it be cis? Yes, it could be, so it's stereogenic. It can be either cis or trans. Is that stereogenic?
Yes.
Yeah. Is this E or Z? Because with 2 groups we can use cis or trans. With more than 2 groups on the alkene we need to use E or Z. Is this E or Z? Probably named it. Maybe not. We may not have put it in the name. You sure I named this in the video?
Yes.
You did, but you didn't put
You
your
did.
Do what?
Yeah,
Yeah, I don't think you put yours in part of it.
Yeah, but there's no E.
that wasn't until later on, but we got to.
Did I tell you that we would later do it?
Yeah.
It seems odd that I would not have mentioned E or Z when we were naming this compound.
Yeah.
Is this E or Z?
Z.
Z? Is this same sign? Who says Z? Anybody say E? Okay, how do we do this? What's high priority group on this carbon? Chlorine or carbon? Chlorine. What's high priority group on this carbon? Carbon or H? Carbon, indeed, they're on the same side. Z. That's the Z and then the name. Could it be E? Could you draw an E here? An E stereoisomer? Yeah, if you just switch the chlorine and ethyl positions, then it would be E. Alkene is stereogenic. It can be both E or Z. Same as that one. What about this one? Is that alkene stereogenic?
No.
It is not. Two ways to tell this. First off, is it E or Z? What's high priority group on this carbon? H or H?
Neither. I mean, you don't know.
You can't do it, and then there's no winner. That'll tell you there's no E or Z. Also, what if instead of this group going this way, we drew it down? Okay. What if we drew it down? That's the R group coming off. All that's R group. Any difference between these two? No, that's the same compound. It is just turned over. It's not a stereogenic alkene. Again, if you think it is, then it should be either E or Z. Well, guess what? You ain't going to be able to determine E or Z. It's not possible. Because which is high priority, H or H? It ain't possible. You can't. You can't determine it. Okay. These two alkenes are stereogenic. That one is not. You need to be able to determine that. What did we not cover here? Any questions here? Other side, cis trans. Did we do all these below here? Did we do the very last one?
Yeah.
Did we do this one?
Probably not.
I don't think
Oh, we did, because I remember you saying the more it'll end off, like, yeah, just.
you did Z or E.
Like, I know we did, you know. I know you did that one. I remember.
Okay, did we do tamoxifen, breast cancer drug, top right? Did we do that one? Is that D or Z? Okay, seems like we did everything there. Any last questions about nomenclature, EZ? Okay, we can look at that this afternoon. Diastereomers, basically there you go. We've already talked about it. There's some written definition. Epimers, we just talked about epimers, yeah? Type of diastereomer where you have only one change, where you have multiple chiral centers. What's the enantiomer of a compound that has four chiral carbons with configuration being RRSR? The enantiomer would be SSRS, right? If you look in the mirror, everything changes. Is that right? What would be an epimer? Well, that's where you would only change one thing. And many possibilities there. RRSS would be an enantiomer of RRSR. Yeah? So we only change the last chiral carbon configuration. Meso compounds, we covered that. A compound is not chiral, despite having chiral centers. That's because even though it has chiral centers, the entire molecule is actually symmetrical because it has a plane of symmetry. Easy to see planes of symmetry in Fisher projections. Easier. That's one reason we like to be able to draw Fisher projections. Since it's not chiral, it would not be expected to be optically active. Because only chiral compounds rotate pp light. Meso compounds do not, because they're not chiral. They're symmetrical. So the light is going to interact with one portion one way and then the other portion the other way, and you're going to get no net rotation. Symmetrical compounds do not rotate pp light. Finding Waldo, planes of symmetry. Let's look on the page here. I sent the key out to this, but we'll work some of these here. How many chiral carbons in this drug here? Zocor. So with cholesterol. Number of chiral carbons, anybody already have it? Anybody? Anybody got an answer for that one? 7? Seems close. Maybe I'll give you another day to work some of those, and then we'll see if there's any questions about those up there. Let's look here. Identify each of the following as chiral, achiral, and meso. First one. First one, chiral, achiral, or meso. First one. Chiral, achiral, or meso. Why do you say chiral?
Just because you have some of them, you don't want to dash, and I was thinking meso, but they're not the same.
Then what do you want to look for? Do you see a plane of symmetry?
Is that one
Is that a plane of symmetry?
No.
You have bromine 4 and a bromine 4 mirroring each other? No. Certainly that's not the plane of symmetry. You need 2 bromines over here to mirror 2 bromines over there. There's no plane of symmetry. This is chiral. Where's Waldo, right? You see a plane of symmetry here? Yes, right there. What's the answer? Meso. Why is it called meso and not achiral?
Because it still has.
Because it does have 2 chiral carbons. Most of those carbons are chiral. A compound that has chiral carbons yet is not chiral as a whole is called meso, correct? How about the next one? Chiral, achiral, what? Chiral. I did not see a plane of symmetry. Over here. Chiral, achiral, meso.
Moving on. That's chiral.
It's the same situation as the first one.
Yeah, chiral.
Anybody else? I think it's probably meso too, but I want to draw it in a Fisher projection because it's easier for me to see in Fisher projections. Let's draw this in a Fisher projection. The thing is in a plane. We can look away. Let's make this the ground. With the chlorine going away, what side's the methyl on? With the chlorine going away, the methyl is on the right. I'm just drawing NeCH3. With this chlorine going away, what side's the methyl on? Also on the right. With the chlorine going away and undrawn H's are here, what do you see now? Plane of symmetry. Much easier to see in Fisher projection, yeah? What's the answer? Meso. Because it does have 2 chiral carbons. How about this, how about the next one? Fisher projection? If I draw a Fisher projection, this is the ground. With that methyl going away, chlorine is on my left. I'm drawing H on the right. With this chlorine going away, this methyl is on my. So I got to kind of be tall here, and I'm looking like I'm looking down at it. That chlorine's going away. I'm up here. Chlorine's coming down. It's going away from me if I'm up here. I'm up here. The methyl is on my. I say right. That's left. Coming off the board. I'm up here, off the board is to my left. With the chlorine, the bottom chlorine going away, the methyl is on the left. There's an H going back here, it's on the right. What do we see? Okay, here we go. You can rotate fissures. The top carbon and the bottom, they can each be rotated like a clock dial. Alright. Why do you say we rotate this chlorine up so it'll be exactly opposite of this chlorine? Okay? See, when we drew mirror plane, if the top is mirroring the bottom, you got to have a chlorine going straight up and chlorine going straight down. We can rotate this. I'll keep the chlorine down. I actually let me do this, because typically in fissures, you typically want to have alkyl groups at top and bottom, and heavier atoms, like halogens or oxygen heteroatoms, to the side. So let's do this. Let's put this methyl, let's rotate this here. We can just spin all this down here. Top's going to stay the same. We're just going to turn this. The methyl comes down here. Chlorine goes here. And H swings over here. Now the methyls are sort of mirroring, but are the chlorines mirroring?
No.
They are not. And guess what? They never will. You can rotate this all you want, and it will never mirror. That will never be a mirror plane. But I'm telling you and showing you can rotate these. We'll do more rotation. But no matter how you rotate it, you'll never find a mirror plane. The answer is thus what? We're over here, right? This one here, chiral. We can also do that R and S trick real quick. Is this R and S? Chlorine's 1, carbon with chlorine 2, methyl 3, H in the back, this is R. If that's R, it's the same type of carbon over there, carbon with a methyl and a chlorine and an H. What configuration is that? It's also R. How do you know it's also R? Because we said there's no mirror plane. If it was S, that would mean both sides are mirroring. R and S, they're mirroring each other. Because R is looking in the mirror and seeing S. But we don't see that. There is no mirror plane. So it's R. I mean, I'll bet you a steak dinner with a big baked potato on the side is R. You can do it on your own. But that's that little trick. And I guarantee you, if this one over here was miso, I guarantee you one's R and one's S because they're mirrored. The two carbons are mirroring each other. We found that mirror plane. I'll let you do the one over there on your own there, including some at the top. Let's look at these other ones here. Basically, what are we doing? We're trying to find Waldo, because ultimately the answer to is it chiral or not is it doesn't have to be a plane or not. And that's another way of saying, is it symmetry? Is it symmetrical or not? Answer, first one here. Where's Waldo? Or is there no Waldo? Well, there's actually is a Waldo, right through here. Half a chlorine forward mirroring half a chlorine forward. Half a ring mirroring half a ring. Half a bromine back mirroring half a bromine back. Split right through there. If you could take a saw and go right through here, you would have half the molecule on one side and half on the other. Same exact mirroring each other. That's a mirror plane. What is this? This is actually just achiral. Why is this not meso? This compound does not even have chiral carbons. That carbon is not chiral. Does it have 4 different things attached?
No.
No, it does not. This is an interesting compound. It is, there's no possibility of enantiomers here, but there is possibility of diastereomers. What are the diastereomers possible? The possibility here is for us to draw this. What's the difference in those two? Cis and trans. Cis and trans on a ring. Cis and trans are stereoisomers. Same connectivity, just different projection. What type of stereoisomers are those? Are they mirror images? Here, I'll be cis. Consider me a ring in 2 groups cis. You be cis. No, I'm sorry, you be my mirror image. Okay, I'm cis, what are you? Cis, okay. The mirror image of cis is cis. Let's do this. I'm trans. You be my mirror image. I'm trans, my mirror image is trans. Put your other arm forward. If you ever look in the mirror and your image is doing that, you got some problems. You got a bad mirror. The mirror image of trans is not cis. Okay? Are these mirror images? No, they're not, but they are stereoisomers. So what's the relationship? Diastereomers. Diastereomers. Okay, I told you over here, types of diastereomers, cis-transers types of diastereomers, erythrothreos types of diastereomers. What terminology is used for enantiomers? RNS or DNL. Okay? But these are mirror images. These are clearly not. Ultimately, this compound here has possibilities for diastereomers, but it does have no possibilities for enantiomers. Over here. So that one was achiral. How about this one? Do you see a plane of symmetry? Is that a plane of symmetry? No, if we had a bolded knuckle up here, it would be, but we don't. How about that?
No.
Correct. There's no plane of symmetry here. The mirror image of this is going to be different. It's chiral. How about over here? This is doubly achiral. This has 2 planes of symmetry. One coming right through here. You see that? Half of the same molecule on one side as the other side. There's also a plane of symmetry where? Actually, also right through there. That's 2 planes of symmetry. What do you want to call this one? It's also achiral because it does not have any chiral carbons. That is not chiral. Because if you go this way on the ring, you get the same as you go that way on the ring. It doesn't even have chiral carbons over here. Plane of symmetry right through there. Methyl forward mirroring methyl forward, half a bromine back mirroring half a bromine back. Plane of symmetry. Answer here. This is what we call meso. Because it does have chiral carbon. These carbons are chiral. So look at it. That's chiral, because if you go this way, you encounter a carbon bromine, but if you go this way, you do not get a carbon bromine. So the ring is not the same way from here. But here it is. Because if you go this way, it's the same as if you go that way. Call that meso. Sometimes you may see rings drawn like this. This is a 5-membered ring, where instead of drawn flat on the board, it's like it's sort of drawn like this, with the front edge of the ring coming a little forward. That's why it's bolded. Okay? Can you see a plane of symmetry here or not?
No.
You might want to redraw these. Anybody got an answer for this one? Anybody see anything? That's drawn. There's a plane of symmetry right through here. Can you see that? Can you see 3D? If I redraw this, you can redraw this. How about if I do this? Does everybody agree it's a 5-membered ring? Does everybody agree that the bromines are adjacent carbons? They're vicinal? Also, are those bromines cis or trans? This is not exactly axial or equatorial, but can you see that they're both kind of up? They're cis. We could redraw that another way. What if I drew it like this? Bromine here and make it cis. That's the same compound. It's a 5-membered ring, bromines next door to each other, and they're cis. Now can you see a plane of symmetry? Yeah, it's right through there. It's supposed to be right through that carbon. Right through that carbon in between these two. That's what I tried to show here. Another way we could do that is just turn it a little bit. You can still draw the bromine sort of like up. But if I do it like that, can you see it? Again, I'm having trouble going right through that carbon. It really looks like it now. Right through that, okay? That's what I'm trying to show here. Do you kind of see how if we just turn it, coming through there between the two bromines? That's what I originally tried to show. Yeah.
What if we put the bromine, so that one of them is on the top and then one of them is on the side?
You mean here?
Yeah, here, and then,
Well, I think you should also be able to see it. I mean, that's the same compound.
no, but putting one of them on the carbon of the.
Here?
Right, yeah. 'Cause
Well,
that's what I
that
kind
would
of,
not be the same compound, because they're in a 1-2 relationship.
that's not,
You want to put the,
yeah, that one up there.
okay, well then, that's the same compound. It's just you got to see that this ring is really symmetrical, and not as I drew it, but it should be, and there it's coming right through here.
Oh, gotcha.
So you got to kind of see that there. And that is a plane of symmetry. So what do you want to call this? It's actually meso because those carbons are chiral. What about over here? I'll let you look at this on your own, but this is chiral. You're not going to find a plane there.
Because one's not trans.
You can maybe say I'm going to slice right through the bromines. The problem is you'll have 2 carbons on one side and 1 carbon on the other. Look at that. You can look for 100 years. You're never going to find a plane of symmetry there. That means the mirror image would be chiral, would be different. You have to trust that. If you cannot find a plane symmetry, that tells you that the mirror image is going to be different. That is just a rule of nature. Okay, we need to work towards questions like this here. That is doing alkene reactions, but also fully assessing stereochemistry of the product with terminologies, also maybe drawing Fisher projections of products, and answering questions such as that there. All right, we need to work towards that. At this point, let's take a 2-minute break, and then let's look a little bit at alkene reactions, back there a little bit, and try to pull things together a little bit more. I'll also go up and get a couple of handouts. Yeah, I think that's about it. Yeah, 5 or 6. Somebody want to be in charge of erasing the board and clean the erasers while I'm going? You can use whatever you want. I got spray, I got an orange cloth.
I don't know why. I will never really just have an AG for that. They like that often do sometimes. I really cannot find that is so hard. Like if AG is working through the rest of well, no.
Extra handout. How'd the board do? Reduce the spray or not?
No.
Okay, guys, how we doing? We have alkene nomenclature, including EZ, alkene reactions, we got Stereochem, and some miscellaneous things in there, such as thermodynamics and kinetics, reaction force and diagrams. Okay, the purple we're going to have to get to applying stereochemistry to alkene reactions. And for practice, please try that problem right there. Okay? Very important last page here. Stereochemistry, there's lots of applications here. Page over here. You know, something like this, you can say, is this really S? Ibuprofen is S. Well, you can make sure you can see that that is S configuration at the chiral carbon. Fluoxetine, aka Prozac, is actually an R configuration. Only R is given as a drug. Make sure you see that that is R, so we can use that as practice. How many chiral carbons here? This is called, I've never pronounced this drug, Jeftana? Jeftana? No. Prostate cancer, that's a beautiful compound, isn't it? With a complex ring system, that's not just a simple molecule there. Like, the above is pretty simple, this is more of a complex molecule. Still has functional group, right? What is that, a ketone? Ester? Stereochemistry? How many chiral carbons? Look at the name of this compound. Could you name it? Well, there's the name. Every chiral carbon has to be identified. And in that drug, every one has a precise configuration. There's your name. You could all name that, right? No. That'd be quite difficult. That is not a standard thing. So is this compound R or S? Well, R and S refers to an individual carbon. So this compound has many R and S. Question though, is this compound D or L?
It says L.
Because D or L is for the compound as a whole. This compound is either D or L. It either rotates. First off, is it chiral? Or can you find a plane of symmetry? Do you think you're going to be able to find a plane of symmetry here?
No.
I mean, it only has one terbutyl group. So this is always not a plane of symmetry because you got to have the terbutyl group over there. And if it was a plane of symmetry, it would have to go right through the terbutyl group. You ain't going to find a plane of symmetry. How many stereoisomers are possible? Could you do that? You should. How many stereogenic sites? And then it's 2 to the end, right? Some data about this compound. Specific rotation, which we'll talk more about this afternoon, is negative 32.9. Is it D or L? I mean, it's L. D or L is for a compound as a whole. R and S is for individual carbons. And by the way, is it only carbon? No, many other atoms can be chiral too, but we only focus on carbons really here. There may be a question or two or an example of some other type of atom. We could actually have a chiral sulfur or a chiral nitrogen. Those are more rare at the introductory level. basically, this has an enantiomer. And an enantiomer will rotate how?
32.9.
Positive 32.9. It would be not L, but it would be D. Okay? And methanol, usually when you have a rotation, you get the solvent in which the compound will dissolve. Because rotation can be solvent dependent. It's usually done in solution. It's dissolved. That shows how an enantiomer may fit into one glove but not the other. That's analogous to me showing you how my hand will fit into this, but this hand won't. But that's important for how most drugs, particularly a chiral drug. In this case, the R enantiomer fits into the chiral receptor, but the S enantiomer will not. And even if you try to rotate it, it never will. Because if you rotate it, then this group will be going back. Okay? There's questions all over the place. We don't have time here, but they're for you to use and test your knowledge and ask questions about it, etc. Its applications, again, drugs. I like this one here. Ever heard of Levaquin? Have I ever heard of Levaquin? Antibiotic? No? It's a fluoroquinolone. It's called a quinolone ring at the ketone. It's got one chiral carbon with a precise stereochemistry shown. Is it R or S? Only one chiral carbon. R or S? Pretty straightforward example. Marfan, you got it? Well, what's high priority group on the carbon? H, C, N? You got two C's. N, correct? What's next? Carbon or carbon? That would be all H's. What's on this carbon? O beats H, so this is 2. Carbon with H's would be 3. That would be 4. And the low priority group is in the back, so what is this? That's 1. What is it? It's S. And only the S configuration is given as the drug. It's called a hemihydrate. What does hemi mean? Half. Every mole of the compound has a half a mole of water with it. Should have saw hydrates in Gen Chem, a lot of salts, some hydrates. Because something about the molecule just attracts the water. And it's almost, you can almost consider it an impurity. But since water is pretty benign, it's an okay impurity. But sometimes compounds just like to trap water. And it's miraculous how it tends to be a certain amount what it traps. For example, sodium sulfide, Na2S. It's a miraculous, but when you buy this stuff, you get 9 waters with it. It just traps 9 waters. Certain IMFs that just leads to that crystal forming with 9 waters associated with it. Amazing. Why not 7 or 6.5? It's always 9. And this, something about the molecule just likes to trap a half a mole of water with the crystal. Now, sometimes you can dry it. I mean, you can get anhydrous salts, and we're going to use anhydrous sodium sulfate. But sometimes it's hard to remove it, or you may heat so much that you destroy the molecule, and they just decide, hey, we're just going to go with half a mole of water, and we're going to call it a hemihydrate. And that's fine. You just know that the molecular weight has a half a mole of water added with it. Because whatever this is, you have to add, that's 18, so it's plus 9. So, hydrates are often encountered. It's, what did we say, it was S?
Yes.
Okay, is it D or L?
No idea.
D or L?
We have to do an experiment.
You're correct, you have to do an experiment. Or you can look at the name of this drug. And the name of this drug is what? Levofloxacin. What do you think the levo means? Means this drug is actually L. A lot of times chemical information is used in names. Okay? Called levofloxacin because it's liver-rotatory. Kind of sneaky, yeah? Just lots of information in names. Yes, otherwise you would not know because D or L has nothing to do with R and S, right? There's some other things in here. For example, fentanyl. Familiar with it? Very powerful narcotic. Yeah? Fairly simple structure. How many carbons? 2 nitrogens, 1 oxygen. There you go. This stuff will kill you though. Okay? There it is. How compared to heroin? That much fentanyl equates to this much heroin. Okay? Is fentanyl chiral? You can ask all the questions. How many stereoisomers possible? There's another drug over there called omefentanil. Somebody was not that creative with that name because what's the difference between fentanyl and that one over there? It has an OH added and a what? And a methyl added, and they decided to call it omefentanil. Okay? That's pretty creative, right? But you can read about it. Hopefully you have interest in such. This is organic chemistry. I think let's look back at some alkene chemistry. How are we doing there? I was looking through the ones that we did not do, ones that we maybe want to do today. We can do more than later, but I think right here, I don't believe us on the oxymercuration, hydrogeration. I don't believe I did these two here. Is that right? Somebody have products of these? We got an alkene. What are we doing here? BH3 followed by what? A magic step? What is the magic step? It's hydrogen peroxide under basic conditions. I just call that magic though, right? What does this do to the alkene? Because that's the first thing we got. What type of reaction is it? Converting the alkene to what? That's got to be quick, guys. This reaction converts the alkene to what? Type of functional group? Yeah, we're making an alcohol. But what about regiochemistry? Is the OH going to be on the more substituted carbon or less? Is this a typical outcome or atypical?
Atypical.
Atypical. And I'm referring to carbocation. If we made a carbocation, would it be on top or bottom? Top. And then we can envision maybe water attacking carbocation. If you're going to do a standard hydration, that would put the OH up here. And that would be the typical product. This gives the atypical product. It gives the OH down here. That's some of the thinking, thought process you have. Okay? Now your book is going to present it in a certain way. I present it in a certain way. You've got to figure out how you want to know it. So, we can first show it without stereochemistry. And that's the product without stereochemistry. It's the atypical anti-Markovnikov hydration alcohol product. Do you see the new H? We've added water to this product. This essentially hydrates the alkene. There's a lot going on here. That's essentially what happens. It's ultimately a hydration of the alkene to make alcohol. There's a new H here, right? Because there's only one, there's no H. Now there's one there, undrawn. But now let's look at stereochemistry. We've got two groups on the ring. Are they going to be cis or trans? Why do you say they'll be trans?
Because if not, they'll let you leave.
They're what?
They'll be leave, like, they'll go forward.
Well, if they were cis, they'd both be forward or both back. What's wrong with that? Trans is a more favored orientation, but the outcome comes from the mechanism.
Facts.
These two groups will be trans. How do we know that? Well, let's look at the reaction. What does the alkene attack? Attacks the boron, right? And that gives bond to boron. This carbon now becomes tetrahedral. The bond to boron can be forward. And boron is now minus. Plus here, maybe. I don't know. Let's start with that. But it can also be, the boron can also be back. Because the alkene is planar. It's planar. It's walking down the road. Okay? Ooh, a BH3. Bam, the bond is forward. Ooh, a BH3. Bam, the bond is back. And that's 50-50 chance. Because the alkene has two sides. Okay? Now, is this really formed? What do you think is going on here?
She was made.
This is not really formed, is it? What happens at the same exact time that the alkene electrons attack the boron? The same exact time, this shoots an H. I can do it over here as well. When that shoots an H, here's the big question. Boron is forward. After it shoots an H, it becomes BH2, correct? And it's neutral. This carbon now has four things bonded to it, the methyl and the H in the ring. Is that H forward or back? It's forward. Why is it forward? And by the way, since it's forward, the methyl gets pushed back. Why is that H forward? Because it came from the boron. Here we go. I bond to the boron, you throw me an H. Boom. There it is, it's forward, because it came from you. Unless you're going to throw a curveball and it comes around. No. If the boron is forward and the H comes from the boron, it's going to be forward. This is in step one. And what did we just add to the alkene? BH3. BH3. But in what manner did we add the BH3? Do we have an outline somewhere? What color is the outline of the green? How did we add the BH3? Because I'm sure it's got to be somewhere in my hand. It's a concerted mechanism. That is, these two steps happen at the same time. How did we add the BH3? Syn or cis. It's kind of synonymous words. It's a syn addition, which is the same as cis. Syn means same side. You see how the BH3 was added in a syn addition across the pi bond? They're on the same side. Why are they on the same side? Because the H came from the boron. That's in step one. What does step two do? The magic step. It replaces the boron with what? OH. And what did we say about it when you do that replacement? You may not have paid attention to what we said about it. We said, is it in your notes? No change in what?
Stereochemistry.
Right. Just get rid of it, but keep the same stereochemistry. There's your product. Now, if you want to get rid of the H, because we typically don't show them, there's your product. Is it cis or trans? The two groups that are on the ring are trans. Because the OH and the H are cis. The OH and the underone H are actually cis. Well, let me ask you this. Is this compound chiral? Is this product chiral? Yes, it's chiral. There's no plane symmetry. Will we only get that enantiomer, or will we get both?
We get both.
We're going to get both.
We would have the answer.
We get both. How do we get the other one?
If it connected from
Over here. Because if this throws an H, how's the new H going to be? Boron is forward, back. How's the H up here? Back. That pushes the methyl forward. And if you do the magic step, this becomes OH. And if you just erase the H and show it as a line bond, we also get this. What's the relationship between these two? Can you see the relationship? The back bond is the same. Both projections have been switched. What are these? Enantiomers. You're going to get both enantiomers. And half of you know what would be the ratio of these two?
50-50.
It's 50-50 because it all starts with the original alkene. Half the reaction's over here, half is over here. See, when you got a bazillion molecules, as long as you're stirring well, even if you're not, it's 50-50. Okay? It's like flipping a coin a gazillion times. You're going to get 50-50. Give or take 2 6 figs. Okay. What do we call a 50-50 mix of enantiomers? Racemic mixture. Half of you know that comes the other. We talked about it yesterday in lab. No? Okay. Let's go ahead and talk about this terminology here. This reaction gives trans product. See how they're both trans? Does not give cis. There's some terminology we can use here. Is this reaction enantioselective?
No.
What does that mean, enantioselective?
It selects one enantiomer.
What would gender selective mean? One gender. What does enantioselective mean? One enantiomer. Does this reaction only give one enantiomer? No, it gives both. So is it enantio selective? No. It gives both. How about this? Is it diastereoselective?
Yes.
What could that mean? What is that? What are the choices if we say is it diastereoselective? What could be possible diastereomers here? We've already said it. What are they? Possible diastereomers of the cis and trans. That's the possibility here. Does it give both cis and trans, or is it selected for just one?
It's selected for this one.
It only gives
You said And which one does it give? We've said it many times, it gives diaster selected. Yes. Trans only. Right? So it is di-selected. Di-stereo selected. How about this question? Is this reaction regio-selected?
Yes.
What are the choices? What are we looking at? That's talking about regiochemistry. What is that referring to? Is it or is it not? This refers to where the groups end up being bonded at site. And when you have an alkene, it's either carbon, okay? Does the OH end up on either carbon of the original alkene or only one carbon? Only one, only the less substituted. Do you get any product with the OH here and the new H there? Like this? Original alkene, but the groups are added like that instead? Regioselected? Yes. What do we call the regiochemistry here? What term did we use? You could say it did this. What regiochemistry term did we use here? So kind of reversed, atypical, but it was a name. It was a Russian chemist.
Oh, Markov.
Okay. And we call this reaction anti-Markovnikov regiochemistry or outcome. There's a couple of Russian chemists in the late 1800s. They weren't drinking vodka, they were working in the lab. Okay. Markovnikov, Zaitsev, a couple of others. These are terminologies for assessing reaction outcomes of different things. Stereochemistry, regiochemistry. All right, and that is sort of discussed on the last page. Purple. Right here. Try this one here on your own, though, and answer some of the same types of questions, okay? This type of question is sort of the ultimate here, pulling all of our information together. Will tend to be one of the more challenging questions, but everything's pulled together here. Both the alkene reaction outcome and the stereochemical outcome. Very doable, though, okay? Do we have a product for the last reaction? What are we doing here? What type of reaction is this?
Oxymercuration.
What type of general overall reaction outcome are you doing here? Oxymercuration does what to the alkene? It's a way to hydrate the alkene. But instead of just using aqueous acid, it's some fancy reagent. But ultimately, it's the hydration of the alkene. What do you know about regiochemistry of the oxymercuration? Markovnikov. Standard. That is, the water kind of ends up the same place as if you had a cation and water attacked it. Where would you make cation? Top or bottom? Top. And so you can envision sort of water bonding there. Now the mechanism is much different from that, but that's sort of the standard thinking. And so down here, I'll redraw this. You can draw it fresh. What's the product down here look like? Right there? You see, if you try to make your bonds connected, it gets worse. Sometimes you just say, hey guys, that's a 6-member ring, right? Okay. All right. Is that the product for that reaction? Did we get the regiochemistry right? Is the OH bonding in the right region? Site? More carbon hydration, yes. Okay, is that product chiral? It looks like those are in the, that's the same carbon, right? Is that chiral? No, it's not. There's a plane of symmetry right through there. No, I didn't even show the tetrahedral nature of this. I could have shown this forward and back. Sure. And I could have shown this like this as well. I could have shown that forward and that back. What's the point? Are those different? You got to know that that's the same compound. How do we know it's the same compound? Because it's not chiral. That's just like me showing you two paper clips and saying, hey guys, I'm just making paper clips. It's just one compound. Just show, how about we just show one? Right? I could keep talking about this. I have a sense that many of you don't understand that this is the same compound. Everybody good here though? Okay. We need to move ahead. It's very important to realize that that's the same compound. And a lot of times when it's not chiral, you don't even show the projection. It's like, you can show it however you want. And so a lot of times we just show it, I mean, it doesn't really matter. You can show it forward, back, whatever, it's all the same. So that's why we often don't show it in this case. Okay? We still need to pull some things together, but in terms for the quiz tomorrow, any last questions? So at this point, before you do more work and incorporate stereochemistry, question?
So for this one, was it a column?
Yes, that compound is not chiral, which means achiral. A means not.
Feels like this tomorrow covers stereochemistry.
Largely alkene reactions, including E and Z terminology. May include stereochemistry, but it will be more of the introductory stereochemistry. The things we're kind of moving into now, I guess they're more advanced stereochemistry. We'll save that for our next quiz, which will be on Friday. All right. So possibly some of the introductory basic stereochemistry, which we looked at mostly yesterday. Largely alkene reactions and possibly reaction according to diagram type stuff, that handout, with the thermodynamics and kinetics, and the EZ nomenclature type stuff in that video. Okay? Good? The last major topic of test 2 is alkyne reactions. That was a handout from today. Alkyne reactions shown here. We need to cover, before we cover this, there's one other alkene reaction we have not covered yet. Yes, we can cover that. I mean, we have enough time to do it right here. In the white handout, alkene, what our last reaction, including this would be C on the green outline. C. You almost let me forget this. Kind of wish I did it in lab yesterday, but didn't do it. And let's look at this. This is hydrogenation of an alkene. White handout, alkene packet here. This reaction is shown down here, where you have an alkene. It will react with hydrogen, not Br2, not Cl2, but H2. This requires a precious metal catalyst, such as palladium, platinum, nickel, or rhodium. Okay? Precious meaning more expensive. Your sort of main cheap elements don't do it. Like zinc or iron, they typically do not catalyze this. More the expensive precious metal catalysts that will do this. Catalyze this. What are we doing here? It's one of the easiest reactions we'll ever do. We're adding an H to each carbon. Okay? And we're saying we're hydrogenating the alkene. Now when you add H's, it's also called a reduction. So you can call it that as well. There's a new H here and there's a new H here. The alkene is thus converted to a what? It's just converted to a plain alkane. There's no bromines, there's no OH, it's not an alcohol. Okay? Do we have to worry about regiochemistry? Which carbon gets a new H? Both. So do you have to worry where? There's no regiochemistry. How does this mechanism take place? It's not an ionic mechanism. What's an ionic mechanism? That's a mechanism that involves ions. All right. And if you look at all of our previous mechanisms, they all had ions. And one of the biggest ions early on was the carbocation. All right. Now sometimes those are not even actually formed, but we had ions a lot. It's not ionic. We're actually not going to show a curved arrow mechanism. It's actually not well known. The mechanism for this is, or the information is, the hydrogen, these round things are the metal catalyst, metal atoms. The hydrogen will sort of absorb to the metal. How? Well, it's not quite known exactly all the full details. At least not enough at the introductory level to make it a simple explanation. But a lot of metals are known to absorb hydrogen. So there's some interaction. How? Is hydrogen polar? There's lots of questions here. But it sort of associates with the metal. It almost starts breaking the hydrogen bonds, almost bonding to the metal. But the pi bond can approach that metal, and here's how I tell you how it is. It's almost like shooting darts now. You're the alkene here, carbon-carbon double bonded, and these H's are just boop, shot in. Now, is that some mechanism? Does that sound scientific? Shooting them in like that? That's what I'm going to tell you. All right? Off the metal surface. You've got to have that metal. It sort of makes it happen here. Importantly, though, because the two H's come from the metal surface, boop, being shot in, and those two sigma bonds are made, in the product, how are the H's oriented to each other? I underlined it up top. They're going to be on the same side because they both came from the metal. Okay? And that's an important thing to know right there. Thus, if you hydrogenate this alkene, which because it's cyclic, it allows us to have some easily identifiable stereochemistry, the two groups, the ethyl and the methyl, will they be cis or trans? Well, they'll be cis only. Why? Ultimately, it's because the H's are what? Because the two new H's came by a syn addition of the hydrogen. Since they're cis, it makes the existing group also cis. They end up being pushed forward to make room for the two new H's coming in from the metal. Cis only. You would not expect a trans product. Okay? By the way, sometimes you may see deuterium here, isotope of hydrogen, sometimes used. It's important to know that both of these alkenes give the same product when hydrogenated. If we add an H here and here, you get that product. If you add an H here and here, you get the same product. Everybody see this? Okay. By the way, it's only one of these. I had a student one time who thought we had to use all of these metals. I'm like, hold on, no. Your choice. Nickel is very common. Palladium is very common, and with palladium you often see carbon because the palladium is sort of dispersed onto the carbon to give it more surface area. Okay? Well, you want to use a very small amount of palladium, but if it's a very small amount, like a grain of sand, it's like it doesn't have enough surface area to react. So you take that grain of sand and you grind it with some inert material like charcoal or carbon, and it spreads that out. Okay? So it's very common to. Nickel is very common. Question though, which route would be more exothermic? Is it exothermic? Well, you could get out your calculator and do bond. What type of bond are we breaking here? Breaking the pi. What type of bonds are we forming? Everybody see the new CH, the new CH? But those are sigma bonds. Breaking a pi, making it two sigmas, does that seem more stable or less stable? More stable. Is that higher energy or lower? Lower. If we're now lower in energy, what happened to the other energy? It's just released, and we call that exothermic. Which reaction would be more exothermic? Top or the bottom? Both reactions give pentane. Which would be more exothermic? Who says top?
I think bottom because it's more stable.
You're right, the bottom is more stable. So rich releases more energy when it goes. By the way, I'm quite happy that you mentioned that the bottom was more stable because a couple of days ago at about 10:20, I think it was, we mentioned how you determine stability of alkenes. And this is more stable, right? Why? Well, I'll refer you back to a lecture a couple of days ago at about 10:20. We discussed that fully and reminded you of how. I mean, we can look at this. By the way, is there any intermediate in that mechanism up there? So these are the questions you kind of have to ask. Wow, I looked at many reactions with intermediates. Does this one have any? No, there's no intermediate up there. If we plot this on a reaction coordinate diagram, let's finish up here. Let's call this A, B, C. If we plotted this, we can label our axes appropriately. We have it's an alkene, arbitrary energy level here, A. Where does C sit compared to A? We said it, more stable. It's got sigma bonds instead of pi bond. It would be here. Okay, where does B sit compared to A? It would be here, right? And then what type of pathway do we have? Do we have an intermediate in our mechanism? No, it's just a transition state, right? This is where the bond is being shot in the transition state. You see those bonds coming in? That's a transition state with a high energy, yeah? Eventually it becomes the same thing. Which reaction is going to be easier? Should be A. I mean, go to the same place. Okay, which is more exothermic? Well, you're just looking at the difference here. That one goes from here to here, and this one goes from here to here. Which one is giving off more energy? And why didn't you stop me? Because B is not in the right place.
Yeah, so I was thinking.
You should have said something. See, I was worried about the clock. This is not right, is it? Which one's more stable, A or B?
B.
B is more stable. That's the thing we tried to say. B should be here, right?
Yeah. I kept saying, I'm not always saying that.
Right? Which one gives off more energy when it comes to this down here? A, because it's sitting higher to begin with. Right? Yeah? Which reaction is more exothermic? The top one. So that's assessing reactions and understanding how you can use reaction force diagrams to organize your thoughts. Okay? A lot like when I asked you to graph hybridization. To me, it's just a way to get everything. Okay? A systematic way to approach answering questions. Okay, there's been many things around. There's the next page here we need to look at. Now, tomorrow after the quiz, though, we'll be mainly moving into that Alkene handout. This afternoon, we'll do some stereochemistry with the second lab group. Have a good day, guys. See some of you at 2:30. 2:30 right here. Unknown report due Wednesday and Thursday in lab.
Email us when you say
That's not, yeah.
I mean, I'm not gonna sit down. Yeah. All right, so